But the question is also down and was involving these are kickbox and does anyone outside? All right, there, I think you can get going.
Good, thanks very much, Francois. Good. So yesterday in the general talk, I talked at quite high level, and I was also quite careful to avoid controversy. So that was kind of the general audience version. This is the mature age version of the talk. And I also want to make it clear up front, please, I don't want to see anything on Facebook tonight, eminent curtain researcher or non-eminent curtain researcher says SKA won't work. That's not what I'm talking about. What I'm looking at is what we've learned from working on the SKA, which is, after all, designed to be a general purpose observatory. So it's got to do a lot of things. And I'm going to look quite specifically at the epoch of reionization and the challenges that are going to be faced by especially calibrating SKA low for that. And looking towards future instruments, at some time, the SKA's Observatory Development Program will kick in, and we'll be able to start looking at the next generation of instrumental upgrades. And I think ideas like this, we need to start thinking about taking what we've learned from SKA low. So the name of the talk is Antenna Design Considerations for Future Low-Frequency Radio Telescopes. As always, I would like to call out a number of my contributors. I won't mention all by name again because I did that yesterday. We'll also mention this particular talk has also been influenced by discussions with Miguel Morales, who of course did some of the fundamental work on the Fourier techniques for the EOR. So the overall theme is to take a look at the performance of the SKA low antennas. That's under construction. And for those of you who weren't in the talk yesterday, it essentially covers the VHF communications band from 30 to 300 megahertz. The design of this system was essentially finalized at least a decade ago back, and the choice of the actual radiating elements in terms of dual polarized log periodic dipole arrays was actually longer than that. It's about 15 years ago. And Stellenbosch had some small contribution to that because I saw a very, very early version of the Scala being measured between the two wings of our building back in about 2011. That system was optimized primarily for collecting area and bandwidth. And some of the issues which since then we've understood are challenges for EOR, in particular frequency dependence of the patterns. These are ideas that have become apparent as work has progressed over the last decade or so. So we're going to be looking at what are the challenges for science cases, and I'm focusing on the EOR, and I'm synthesizing a lot of work we've done over the last decade on this. And I'll finish up the question is there something better one could do if you want to look specifically for an EOR system? And again, please don't confuse this. It's not a suggestion that we rebuild SKA low. This is if we want to do further work or build special parts of it, or indeed build other instruments completely. I'm quoting Miguel Morales there that to date radio astronomy antennas for 21 centimeter cosmology have focused on wide bandwidths, inexpensive collecting area, and smooth beams for isolated antennas. The coupling between antennas has never been a design consideration. And as we'll see, it's mutual coupling that causes the issues. Again, if you weren't in the talk yesterday, the SKA low is in the area of the Murchison, right up over there. I won't run through all the material I spoke about, except to say that this is the radiating element, or sorry, not the radiating, the receiving element is the Scala. It's a dual polarized log periodic dipole array. It's been through a number of design iterations. This is version 4.2 that's actually deployed on site, and it's identical to our simulation model of the 4.1. From an electromagnetic viewpoint, it has some production enhancements. I'm going to skip over that as well. And also the first image of SKA low, you've seen a couple of times. I had it briefly in my own talk. It was shown yesterday in Director Ball's talk, and I don't think we need to talk about that. It's a beautiful image, and it demonstrates some great work by the commissioning team. So many of you are sitting here, and plaudits to the folk at SKA for this. I want to run back to some of the early ideas about SKA low, and I'm going to have to just step away from here and pull the mic with me. So there was quite a large design space which was explored. Some of the first work was the LOFAR design, and LOFAR covered the band by using two different bands. So you've got the low band array and the high band array. And again, there are people like Stefan who are in the audience who were intimately involved with the design. So if I Please correct me if I'm stating something incorrect. But that is essentially two droopy dipoles, and it covers from 10 or 20 megs, depending on which paper you read, up to just below 100 megs, the FM band. And then the high band array, this is actually the Murchison wide field array, but basically a packaged version of that in expanded polystyrene with a shrink wrapper around it forms the high band array. So although we always talk about the Murchison wide field array being very Australian, it's actually an older design. It came, I think, originally from the United States. I know Randall West, before he joined us at ICRA, was working on that in the States. So those arrays are essentially the same thing. There were other ideas around as well. This is an idea from Eloy de Lira-Cido, published in the Transaction Antenna Propagation in 2011. It's called the bow tie low frequency ultra wideband antenna. And it differs from the Murchison wide field array and also the high band antenna in that instead of having a vertical bow tie configuration, it's got a horizontal bow tie configuration. So that was one of the designs that was under consideration. Carrying on, another one that was under consideration were dual polarized Vivaldis. And Ron, you sent me some information this morning which had some other background on this type of system. This is a proposal also published just over 15 years back, just under 15 years ago. It's quite a large structure. It's about the largest dimension, probably in this dimension, is about 1 meter. I can see one of the obvious issues with this is a substantial wind area you've got in this antenna. This may be one of the issues with this. In many ways, the volumes are attractive because unlike a long periodic structure, you don't have this full structure. They transition more smoothly from the high frequency end to the low frequency end. This is wrong. It's not a Rockman lens. Ron reminded me this morning. It's actually a Lüneburg lens. There's one picture extant of this of my predecessor, Peter Hall, somewhere I think in Russia, where this was considered. There was a massive structure several meters across, made of dielectric, and there were problems with the LNA feed, and of course, it would have had a massive wind resistance. Here's another idea. This is the Bighorn design, which Martin Sokolowski at ICRA developed. Essentially, it's a log periodic, it's a 3D equiangular antenna. Again, you can see there are some production issues with these, although whether they're any more serious than the production issues of the dual polarized log periodic, I'm not sure. Somewhere around 2011 and 2012, the Scala antenna became kind of the design reference, and there was never really, nobody went back and looked again at the antenna design after that. A couple of things happened with SKA, which imposed additional challenges. The early specs were essentially about a 4-to-1 bandwidth, perhaps a little bit more than that, from 70 to 350 megahertz. Around 2015, that was dropped to 50 to 350 megahertz. And there are good reasons for that from the viewpoint of maximum possible bandwidth. However, if you think that through, this still had been occurred in essentially the same ground plane. The size is constrained by the primary beam. You don't want it to become too narrow, or you can't do wide field imaging. So the bottom line over here was that the bottom boom length stretched out by about 40%. And if you take a look at the layouts now of the Scala antennas, you can hardly walk between some of them, and that's because fundamentally of this. And it means that the mutual coupling was greatly increased, especially at the lower frequency end. At that same time, there were some other ideas knocking around about how to configure these. One was a sea of antennas idea, and people at Ashford, I think, and Cambridge and Falk looked at this. The idea there was just you had this massive section of antennas at the core, and you then select out which ones you wanted. That was rejected because it was too expensive signal processing. So eventually, the Scala was adopted with this longer boom and with this constrained randomization, and that then became the design reference for SKA low. So here's a picture. This is Maria Grazia-Lobato when she was still at SKA low. She's making adjustments to antenna. I showed this picture yesterday, but here you can see how close many of these antennas are located to each other. The idea was that by having this quasi-random configuration, the grating lobes would wash out. And by and large, that's true. And Lewis talked quickly about rigid rotation. What has happened with the actual station layout now is that all the layouts are the same, but they're rotated in this sense over here. So you no longer have a north, south, east, west beam. It's counter-rotated electronically, and Randall and Gandhi did a lot of work on that at SKA. As I mentioned, this additional bandwidth meant antennas being very closely located with a lot of mutual coupling. I would also just quickly mention, although not directly relevant here, there was also a proposal to use a hybrid beamforming type approach, similar to what's used in LOFAR and also the MWA. The idea with that was to have the first stage being an analog and the second stage as being digital. The issue with that is that you can only form one beam at a time, and like the Embrace system, which actually was multi-beam, that was a slightly higher frequency, that had to actually have duplicate analog electronics. I won't comment on this. Digital design is not my real field of research, but the fact that the SK has gone for this all digital does mean that it's probably future-proof and it's probably a good idea despite the extra cost. We've also spoken about design trade-offs, and Ron picked up on these again this morning. Because of the very wide bandwidth of the system, you're actually dealing with a system which has all the issues of both a dense array and a sparse array because it transitions from being dense to sparse. And there's not much you can do about that. You've got a very wide band array and you have to deal with both of these. And as I mentioned over here, it's dense at low frequencies, sparse at high frequencies, and the transition frequencies around 100 megahertz. Key expectation was that the randomization would average out the mutual coupling and the differing element patterns. You'd be able to do a good approximation with the isolated elements. Now I'm going to dig into these patterns again. I showed these yesterday. This is the isolated element pattern of a scala 4.1 to 4.2. The production model is the same. This is on its own, on its ground plane. Superimpose all the embedded element patterns, which I discussed quickly yesterday, and you get this is the station being phased up to, or weighted to weighted zenith. Again, I showed this result yesterday. I had a number of questions about how do these beams become so narrow? Why do they look like they look like? These, I think, are linear, not logarithmic, but the bottom line is still, these are very distorted patterns. It's not always this bad. 70 megahertz is a particularly bad frequency where this is at its most prominent, but there are other effects a bit higher in frequency which have similar results. This again comes from rigorous electromagnetic simulation, and it's clear evidence that the assumption that all the beams are nice and smooth and can be well approximated by some pretty simple parameters is not going to work in some cases. I also mentioned briefly yesterday, how do we make sure these patterns are correct? Yesterday, I talked quickly about some UAV measurements. There are other ways that also can be done. And Dirk and his team, Randall and the team, starting out their work when they were at ICRA and now continuing that at SKA, have developed a number of techniques where they're able to show using indirect means that these beams are good approximations, and that's done using the entire station as an interferometer. And a similar approach was taken by one of the speakers, Anna, yesterday. And those are the UAV far-field measurements. This is more or less where my talk yesterday stopped. I showed you these three layouts. This is the AVS2. That was the one that was built in 2019 by ICRA and INAF. This is the AVS3 prototype, and this is the quasi or perturbed version of the AVS3, which is also now the production station model. I also showed, sorry, wrong way. What's gone wrong here? Things literally frozen up. I'm just going to restart it. This happened when I was testing it earlier. Right, this is what the beam patterns look. Oh, this is what the station beam looks like. Again, this is now phased up or weighted for direct for zenith. I've got a whole bunch of other data for when you weight it in different directions, but I'm just showing the zenith directions here. Again, if you weren't in the talk yesterday, it's an orthographic view. Zenith is in the middle, and the horizon is on the circumference of that circle. That's the main lobe. The side lobes are dropping down over there. And they follow pretty much the area pattern format that you expect for a uniformly illuminated circular dish. Now we get into the material I didn't discuss yesterday, which is mutual coupling and imaging. So traditionally in radio astronomy, you have visibilities, which in the UV, that's the east-west, north-south baselines as a function of frequency, F, in this axis over here. Traditionally, you do a Fourier transform, a 2D Fourier transform in the sky coordinates, and you then get an image cube, again as a function of frequency in this axis, and as a function of angle and angle. Here we've got theta x and theta y, but this could be right ascension, declination, or theta or phi, or elevation, or azimuth, depending on what coordinate system you're working in. That's actually direction cosine space from the Fourier transform. But the other option is to Fourier transform along the frequency axis. And in that case, you get the Fourier representation or the power representation in a direction which is essentially related to cosmic age. Did I understand that correctly? And again, those of you who are expert in this field may be able to correct or will correct my astrophysics. The idea of this, and it's summarized over here, the epoch of reionization, which is the one that you actually use this for, has a signal which is very deeply below the foreground signal. It's about a 50 dB, about 5 orders of magnitude in terms of power levels below the foreground. Around 2 decades back, and that's the Morales and Hewitt paper I spoke about a couple of slides back, power spectrum analysis proposed to deal with this. The astrophysics is too complex for me to explain, especially because I don't understand it. But the key idea is that the emission from the foreground is spectrally smooth. So in the Fourier domain will be down here. And the Fourier transform of the signal you're looking for, the EOR signal, is spectrally varied and should live over here. And in the Fourier transform domain, with a little bit of allowance for mutual coupling, you should have a window where you can go and detect the EOR. Now, interesting analysis was carried out a few months back at Cambridge. This is a group, this is Eloy and his group, and Oscar O'Hara just finished his PhD on this. What he has done over here is to take a full wave model, similar to the ones I showed yesterday. They use a slightly different modeling tool, but the results have been checked and they're very similar. So they have accurate models of the antenna beams. They put all this into the Oscar simulator, which is a high-level interferometric array simulator. And they put a sky model into it as well. The details are in the paper, which I've referenced over here. It's very recent, a couple of months back. This is what happens when there's no mutual coupling. You switch on mutual coupling. So when you've got no mutual coupling, just an average element pattern or the isolated pattern. Switch on mutual coupling, and all of a sudden, the mutual coupling washes into this area that you are hoping to detect the EOR from. There may be ways around this can be calibrated. I don't know enough about the techniques to fully comment on this, but this looks like it's going to be really problematic. How do we go about trying to improve this? One issue we have is we have no specification on the antenna's properties as a function of frequency. A few years back, Eloy, Randall Waith, and Catherine Trott published a paper which looked at how you can fit polynomials onto beams. That, however, was for single elements. In other words, isolated elements. What I've got over here is the same thing, but now we're looking at the average elements. And if you do a plot where you try to put a fourth order polynomial through the average pattern for the AVS3, which had a particular problem, you see you really are battling, and it's partly because the normalized gain has dropped very badly. This is more dramatically evident on this picture over here. And what you're seeing here are average beams as a function of, this is elevation angle against frequency for the AVS2, the AVS3, and the AVS with the production version, compared over there on the end to the EDA2, which was an array built largely under Randall's guidance, using MW elements on an SKA type layout. So this looks very attractive. The MWA has some other issues, and they relate to antenna input impedance, but it wasn't perhaps given as much attention as it could have been. This is very problematic. We predicted this effect beforehand, and it was actually measured very shortly afterwards. So how can we improve this? One thing to do is to adopt the LOFAR approach. Instead of trying to cover a 7-to-1 band, if you're going to build a smaller section of antennas just for EOR, then go for a band which is more optimized just for the EOR. You can try building things like electromagnetic fences. I've shown ERA over here, which is a curved reflecting surface. It's not really big enough to be called a dish, with cross dipoles as the feed. And there are ideas to raise little lips around here, similar to what's done on Meerkat, in that case to cut out ground reflections or ground noise. And maybe you can cut down on the reflection like that. Something else you could maybe do is design for highly predictable mutual coupling. Ron showed an example this morning again of the checkerboard array, which is used in ASCAP. That's an excellent example, along with Embrace's 20,000 element array, so Astron's 20,000 element Embrace array. These both exploit highly predictable mutual coupling, and they can do it because it's on a regular grid. Could we work natively in the time domain? One of the issues with this is no antenna engineer has ever designed anything in the time domain that I'm aware of. And if you read any of our textbooks, they're all in the frequency domain. Here's a really off-the-wall idea. Dirk and I were at a conference recently in Germany, and someone who's in medical imaging said, well, in MRI imaging, they actually use active cancellation. Could you actually consider doing that to cancel out mutual coupling? Dirk and I think that's probably not practical, but it's an idea. We haven't worked it out. Lastly, could we revisit the antenna element design? A lot of this complexity comes from the Scala, and if one had a different type of structure, the simulations would be more readily doable. Francois, how's my time looking? Well, then I'll wrap up quickly. As we go forward, antenna matching is an issue which always confuses antenna engineers because we're used to trying to match systems. The key parameter with these active low-frequency elements is actually noise matching. And if you noise match, there's a lot of details over here, but essentially what you're trying to do is get an optimum noise match, not an optimum source match. Of course, if these two are the same point, or even better, they're both 0, then it's a really nice design. One reason that you probably want to worry about this, a lot of detail over here, which I've really just put in case someone asks for the slides afterwards. There's some very recent work which looks at mutual coupling between isolated elements, or for instance, NWA tiles. In that, and this is now not elements close together, but ones far apart, the reflection coefficient, the impedance reflection coefficient appears there. So the higher the impedance reflection coefficient, the more coupling you may get between far away tiles. There's a number of points over here that I think would be useful to look for if we go forward. One problem we have at the moment is our whole simulation cycle is way too slow to really put into an optimization loop. We want to be able to use something like surrogate models, and we can't do it with elements as complex as the Scala. We simply cannot come up with a simple network representation of those antennas. We also need to think carefully, what are we optimizing for? Because the optimization for SK low was in terms of gain and bandwidth. Wrapping up, the current design's there, it's baked in and it's going to be built. And for general purpose applications, looking for sensitivity and resolution, it's going to be a really good design. So this is not a criticism of SK low. It doesn't though mean that we can't adapt this. If you look at all the telescopes that have been built to date, like for instance, the Lovell telescope, its dish surface is actually in the process of falling apart, and they built a completely new surface inside it. So radio telescopes can be updated, they can be extended, and they can be modified as the lifespan goes forward. You could look at putting this into later extensions. I think a key thing from an antenna perspective is to have less or at least more consistent and designable mutual coupling. And I presented some ideas that I think could be useful to explore. Finally, SKA has got their hands full building a massive instrument and commissioning the instrument. It's not their job to sort this out and think ahead. And I think that's really going to fall on the universities and research institutes to take further. Francois, thanks very much, and thank you for your attention.
So if Wayne can come up and start transitioning, we've got time for some questions.
I do just have one question. So if you could redo or could add on, what design would you then try to go for? Are you not sure yet? Like, would you try to go for one of those dish designs? Try to go for a more deep type design? And let's say that then, let's say, you know, if you had funding or money, what would you also do differently?
That's a good question. I actually have been posing questions today rather than answering them. So the answer I'm actually going to come up with is I think we understand better what we need to be looking for. But this also needs impact, or this needs input from the EOR community. I mean, we can go and design a new antenna, but if the EOR community, coders here, if we don't get guidance that, this is the band that we think is really important, we're not going to design something that's optimal in that band. I think it needs to be a rather simple antenna, which has slowly varying properties and frequency, and I think it needs to be focused in a band where we're most likely to be seeing the signal. I think that's probably going to work the best. But which of these candidates it is, I'm not sure.
Thank you. Right, thanks again, David. I think we need to transition.
Good afternoon, everyone. My name is Wang Wenjun. I appreciate the opportunity to be with you today. I'm here to talk to you about an optimal strategy of wind field regulation for large fully steerable radio telescope. The contents of my pre is divided into 4 parts. First of all, background. The radio telescope antenna is a large scientific device for observing and studying the radio wave radiation of astronomical objects. With the continuous advance of the process of revealing the truth of the universe, driven by the grand scientific goals, mankind continues to research antenna with large size and higher frequency. In the process of developing this perfect large-scale telescope, a great deal of scientific thought and engineering technology have also been greatly advanced. Taking postal observation as an example, the following is the error formula for radio telescope observation of pulsars. And it can be seen that the accuracy of pulsar observation is closely related to the observation duration, gain, and the noisy temperature of the radio telescope. In order to improve the accuracy of pulsar observation, it is urgent to longer valid observation duration, larger equivalent physical aperture, higher surface accuracy. The antenna is subject to complex environmental influence and gravitational deformation during the service, which lead to a serious deterioration of the antenna's electrical performance. Development trends and performance metrics are both former the primary contradiction. It is a big challenge. In order to guarantee the performance of large reflector antenna, there are a series of innovative methods such as optimal design of structure, electromechanical coupling, active surface, azimuth driver system design, rhythm, and the application of new materials. Wind is an important environmental factor causing the point errors of telescope. Due to the transient time varying characteristics of it, the wind field information has already changed when the wind disturbance control is carried out through the server system. Therefore, scholars have carried out a lot of research on the influence of wind disturbance on telescope, and the current situation are as follows. About wind farm analysis, there are 3 points. On-site measurement, wind tunnel experiment, numerical simulation. About structural response, data collection and statistic analysis of sensors arranged on the reflective surface are carried out. The wind effect of antenna is obtained by the means of pressure measurement, force measurement, and speed measurement. The wind coefficient and the wind pressure distribution of reflective surface and different azimuth position are simulated. About anti-wind control, there are some advanced control algorithms, such as PID, PI, LQG, ESO, temporally discrete predictive control. However, due to the time lag of the control system, the anti-wind disturbance effect is average. So we innovatively process an active regulation strategy for wind farmers at antenna stations, and further invent an optimal strategy for wind fire regulation aimed at mitigating wind load effects by optimizing the structural parameters of wind regulator. The key to the research is to design the wind regulator scheme according to the special topography and the geomorphological environment of the radio telescope site. The second part is the methods. On the basis of determining the morphological structure and the spatial layout of the window regulator. Further optimization research is carried out to the structure parameter of the window regulator that can minimize the influence of window load on the reflector. First, filter out structure parameters with critical impact. Then the surrogate model between the structure parameters and the window force is constructed. And the optimization algorithm is used to obtain the optimal structure parameters values of the window control device. Part 1, the case square of two-factor design is used to quantify the effects of each factor on its interaction on the investigation index and provide information on the main influence factors and the interaction. The sensitivity of different structure parameters was determined by correlation coefficient and analysis of variance. The closer the absolute value of the correlation coefficient is to 1, the higher the correlation degree. In the analysis of variance, was considered to be the significance factor. This is correlation coefficient. Part 2. Firstly, the finite element modeling of the antenna is carried out. Secondly, the calculation domain of the flow field is set according to the diameter of the antenna. Finally, window coefficient is calculated, and the window force is obtained from the wind speed variable. The part 3, safety settings. The RANS method was used for simulation, and the SST model was used for the turbulence model. The calculation formula of turbulent flow energy, dissipation rate, and the specific dissipation rate of the SST model is as follows. Turbulence in density boundary condition consists of turbulence entry scale and in density. And the picture shows the mesh independent verification. The third part is simulation. This study takes the world's largest force durable cheetah radio telescope located in Xinjiang, China, as an example. Since this telescope is still under construction, a 30-meter experimental telescope on its site is used for the structure and the magnetic analysis. This sheet shows the specification of QTT. The key factors are sampled by Latin hypercube to determine the parameter space, and then the window force is obtained by modeling on the simulation of each set of test parameters. The surrogate model between the structure parameters and the window force and the reflector is constructed. The arithmetic optimization algorithm and the surrogate model are used to optimize the structure parameters, and the optimal structure parameters value are obtained. And we analyze the situation without a window regulator and with a window regulator. The upper two rows shows the window pressure cloud diagram, and shows the structure deformation cloud diagram. It shows that with the window regulator, it has decreased the window pressure and decreased the structure deformation. and decrease the 0.02. With the wind regulator, under the northward wind, the wind force dropped by 90.8%. The IMS decreased by 67.2%. The 0.0 of azimuth decreased by 86%. The 0.0 of elevation is reduced by 70.6%. Under the southward wind, the wind force dropped by 87.1%. The IMS decreased by 70.7%. The 0.0 of azimuth decreased by 89.5%. The 0.0 of elevation is reduced by 24.3%. Finally is the conclusion. In response to the wind disturbance problem encountered by radio telescoper, a wind field regulation strategy has been designed and a multi-field coupled joint simulation has been performed. The correlation model between the structural parameters of wind regulator and the wind force and the reflector is established, and the optimal solution of parameter vector is found by using the optimization algorithm. The optimal structural parameter of wind regulator are selected, and the wind resistance effect of wind regulator is verified, which confirms the theoretical effectiveness of the wind regulator. About the future prospects, there's 2 points. Real-time monitoring. Developing a real-time monitoring system for wind farms, dynamically adjusting the angle of the wind regulator and the other characteristic in real time according to the wind speed to maintain the best wind field regulating effect. Multidisciplinary collaboration. Cooperate with experts in fluid mechanics, computer science, and other fields to jointly develop more advanced technology to change the wind direction and reduce wind speed to ensure the observation performance to radio telescopes. That's all. Thanks for listening.
Any questions?
Yeah, cool talk, thank you. The depth of the turbulent region is directly proportional to the wind speed, right? So what wind speeds this for?
Sorry, I can't listen clearly.
That was unclear to me. What wind speeds? How fast was the wind in your simulations?
Wind speed.
Yeah. Oh, there it is, bottom left, meters per second. 7 to 10. Okay, thank you.
Oh, thank you.
So as you said, you've run some simulations, done some real data, and you're trying to future-proof it, like the future-proofing of wind regulators. Is there any call of concern that global warming and other climate factors may change these wind patterns and strengths that you might have to then re-simulate?
Sorry, I can't understand.
Is
slowly.
climate change an issue with the winds changing?
Winds change.
Yeah, will the wind patterns change and will you have to redo simulations because it affects climate change, or is it's probably a bit too much of a question?
I mean, I guess it would be related to the wind speed range, right? So if that changes, then you have to rerun it.
Wind change.
Yeah. So the question's about climate change.
Climate change.
Yeah. So the winds will change over time, right?
Now we still don't didn't research it.
Yeah, okay. All right, thanks. I think we need to move on to the next talk. Thank you very much. Now, if I understand this correctly, this is pre-recorded.
Here I intend to present a brief outline of the video package to model the end-to-end frequency of the correlated beamforming radio telescope. I present the motivation for developing an end-to-end model for the correlated beamforming signal chain. Next, I'll briefly explain why the video package is being developed while there is an existing MATLAB model. I'll go into details of two key aspects of the model. First, the tensor generation, and second, optimizing with the multiple dispatch and speed. Finally, I conclude with the summary and discussion. We at the Wordsworth Astronomy and Astrophysics Research Center of the National Research Council of Canada have been involved designing, implementing, deploying coordinators for the radio telescope over the past 7 decades. For the past 3 decades, our involvement with digital coordinators includes the space DLTI correlator and the wider correlator for the expanded very large array telescopes, which were already delivered. We are currently involved with the correlation beamformer for the mid-frequency telescope for the square kilometer array phase 1 and the advanced technology alpha correlator for the alpha wideband sensitivity upgrade. In earlier implementations of digital correlators, the correlate and segment architecture, which is commonly known as XF architecture, was utilized due to its algorithmic simplicity and the effectiveness of low dynamic range input. However, the most modern correlators are based on the segment and correlate FX architecture. Despite its greater algorithmic complexity, this architecture is preferred because it scales better with the number of antennas and bandwidth. Additionally, it offers improved suppression of radio frequency interference and the capability to achieve non-uniform spectral resolution. This diagram shows the functional architecture of the correlator beamformer for the SK mid-frequency telescope. Note that the key signal processing modules for the different observation modes include different analyzers, tunable filters, resamplers, beamformers, and cross-correlators. For the FX correlators, which involve multiple processing stages before performing correlation and beamforming, end-to-end models are highly efficient. These models provide a comprehensive framework for understanding how different modules interact and influence overall system performance. This understanding is crucial for diagnosing and resolving issues during both the development and deployment phases. Previously, end-to-end models for the SK mid-CBF and the SK low-CBF have been developed using MATLAB. These models have been utilized to evaluate the performance of the proposed signal processing architecture against the requirement and its robustness against radio frequency interference. However, sharing these MATLAB models is challenging due to strict licensing requirements, which hinder collaboration among developers. This limitation further motivated us to develop the model in an open source language like Julia. First released in 2012, Julia is considered the new biscuit on the block for scientific programming that aims to solve the two-language problem by achieving both productivity and performance within a single implementation. It utilizes dynamic compilation and multiple dispatch functions to optimize performance. Since its inception, the open source programming language has facilitated a robust built-in package management system that allows easy collaboration among developers. Over the years, it has gained many devoted developers in various branches of science, mathematics, engineering, and finance. Julia's package ecosystem continues to grow, providing a wide range of tools for public use and enhancement. Particularly, Julia's multiple dispatch feature is one of the main reasons for its effectiveness in scientific computing, enabling functions to adapt their behavior based on the types of all their arguments, fostering highly expressive and flexible code that naturally handles diverse scientific data that facilitates straightforward extension of existing functions to new data types without altering the original code. Also, a new model-based simulation environment called AD has been introduced by the Julia creators that nicely integrates with Julia. The first key feature of the Julia package that I present today is the test vector generation for end-to-end simulation of correlated beamforming. In aperture synthesis imaging, it requires the generation of coherent wideband phase signals with continuously time-varying delays that correspond to the rotation of the Earth to represent celestial emission. Additionally, it requires the generation of uncorrelated wideband noise to represent receiver noise, as well as both narrowband and wideband RFI with various modulation schemes. It has been shown that the coherent wideband pseudorandom signal generation requires an inverse discrete Fourier transform at non-uniform interval. There are multiple Julia packages to approximate the non-uniform inverse path Fourier transforms at arbitrary precision. Among those, NFFT-JL offers a native Julia implementation, whereas FFT-JL and non-uniform FFTs-JL offer wrappers in Julia for optimized C++ functions. To evaluate the accuracy and the execution time of these different implementations, 65,536 pseudo-random samples have been evaluated at sample points that are uniformly distributed with plus or minus 2% of the nominal. The Julia package benchmark tools has been used to estimate the execution time with higher reliability. The accuracy is measured against values evaluated with the direct evaluation of the inverse discrete Fourier transform, which took around 198 seconds. The evaluation time and the normalized RMS error between each of the non-uniform FFT evaluations and the direct evaluation are listed here. The evaluation time and accuracy of the MATLAB implementation of the FFT are also listed here for comparison. Here, the top two figures show the real and imaginary components of the pseudo-random test vectors that are evaluated with direct implementation of the inverse discrete Fourier transform and approximated non-uniform inverse Fourier transforms with NFFT-JL, FFT-JL, and non-uniform FFTs-JL respectively. The real and imaginary components of the differences between the direct evaluation and the approximated evaluation are also shown in the bottom four figures. The second key aspect of the Julia package is the optimization of the function using the multiple dispatch feature. In implementing channelizers, tunable filters, resamplers, beamformers, and cross-correlators, specific methods are deployed for the specific combinations of real or complex valued inputs and coefficients, as well as for different configurations. First, this feature is exploited to process and evaluate the performance for different low-precision floating point data points. This includes float 16, vFloat 16, TensorFloat 32, and float 32, as well as POSIT 16, POSIT 32, linear taproom 16, and linear taproom 32. Note that POSIT and linear taprooms are second-order floating point number formats, and their arithmetic operations are implemented through corresponding Julia wrappers. The oversampled polyphase filterbank function was verified through numerical simulations using the test signals made of sinusoids with known magnitudes and phases and represented with float 64 format. The criterion is to compare the magnitude and phase of the input sinusoid at a specific frequency with that of the corresponding channel. Correcting for magnitude variations due to passband ripple was necessary before comparison of the magnitude. Test signals consisting of uniformly spaced sinusoid of unique magnitude and uniformly distributed phases were generated using the fast Fourier transform. The top row of the figure displays the magnitude and phase spectra of the input segmented into 30 channels in red, alongside the results from the OSPFP function in blue. The bottom row of the figure shows the difference between the input and output magnitude and phase spectra after correcting for passband ripple. Note that to align the input and output phase spectra, the output sample sequence must be shifted to account for the propagation delay through the polyphase filters. The 70 dB suppression of aliasing signal and approximately 0.0001 radian phase error indicate that the OSPFP had been implemented correctly. This diagram shows the difference between the input and output magnitude and phase spectra, post pass band ripple and propagation delay correction, where both the data and coefficients are represented with float 32 format. The results are almost identical to those of float 64 representation, indicating little to no sensitivity loss due to the reduced precision. This diagram shows the difference between the input and output magnitude and phase spectra, post passband ripple and propagation delay correction, where both the data and coefficients are represented with float 16 format. Here, the stop band attenuation is reduced to about 29 dBs, and the level of phase error differ between the channels. For applications for radio astronomy, such variation may lead to bias and therefore need to be handled accordingly. Similar behavior has been observed for the representations with POSIT 16, linear Tarkum 16, and TensorFloat 32, respectively. In summary, having an end-to-end model for correlated beamformers in radio telescopes is beneficial. Such models can be used to confirm that key performance requirements are met early on. The Julia programming language has turned out to be an effective platform for developing advanced signal processing systems for modern radio telescopes. A comprehensive package is being developed to perform key operations such as channelizing, resampling, beamforming, and cross-correlation. This package will also include functions to generate test signals with time-varying delays and to detect and flag RFI. The growing number of Julia packages enhances data processing and visualization options, with several robust packages offering efficient implementations of the non-uniform discrete Fourier transform. Julia's modularity allows for easy integration of the functions handling various data types, although there is still room for improvement in speed and quality of its protein features. Thank you very much for your participation. Again, I apologize for not being able to present this in person. If you have any questions, please email me using the shown address.
Okay, I'll allow you a little time to type that email. Otherwise, we're kind of back on track, so we can move on to the next session. So, Chenya. Morning before the end of the 20th. If this works. Yeah, I'm gonna have to get them to come through and hope that someone's stuck. Give me a minute, I'll pull the, there we go. Thanks, Paul. Putting up some big populations, we'll be back once. Might be that we're starting early.
Potentially. Maybe I can do some USB. Potentially, do you have it? Seven. This one? Oh, yeah. Oh, sorry for the delay.
It's actually okay. We're right on time now. So,
Okay, okay.
so you're good. You don't have to rush or anything. Just...
Okay. Good afternoon, everyone. My presentation is about a single app soap-based 4-channel wideband digital backend for pulsar observation. We'll have the following parts. So in the first part is a brief introduction. Now this is a typical pulsar observation system, and the digital backend serves as a bridge between the analog and digital domains. There are mainly two categories. One is FPGA plus GPU hybrid architecture, and another one is FPGA based. So for the first category, some examples are HiPSR, PAX UWL, and QTT UWL pipe. In this architecture, FPGA serves solely as polyphase filter banks, and we need a GPU array such as the Medusa to process the subband data. And this architecture are potentially expensive and has high power consumption. Another category is FPGA based. Some examples are PDF-B4 with a maximum bandwidth of 1024 megahertz. And our team's previous work is the SU PSR version 2 with a bandwidth of 1.2 gigahertz. And system architecture is shown in this image. And another parser digital backend based on the ZCU 111 featuring 512 megahertz bandwidth is also introduced in the reference paper here. And the reason why we designed a new backend is we have a new requirement to handle 8 gigahertz bandwidth from multiple IF front end. And if we use our old system, which has the characteristics as shown here, this system size can be large, and we need 4 or more devices to handle this total bandwidth. And it is difficult to achieve simultaneous data recording from multiple FPGA boards. So we decided to design this handle this 4-channel in a single RF chip. And the available modes is shown in this table, which has a maximum bandwidth of 2 gigahertz, and the maximum frequency channels is 2048, and the highest time resolution is about 4 microseconds for the 512 frequency channels. So our purpose is to upgrade our previous PSR version 2 digital backend, and we want to design a compact single board design, which has reduced power and size. And we also want to fully utilize the 8 RF inputs of the RF SoC. Next part is the design of our digital backend. So the system structure is shown here, and it has the 4 parts. First is the RF data converter, which has 8 12-bit resolution ADCs, and we use 2 ADCs for 1 RF channel with 2 polarizations. And each ADC has 8 data streams at 500 megasamples per second. So in total is 4 gigasamples per second for 2 gigahertz bandwidth mode. And the next part is the signal processing unit, which is implemented on the programmable logic of the RF SoC. And the processed data is fed into the data recording server through optical fibers. And the whole system is controlled by the processor control unit, which is implanted on the ARM processor system of the RF SoC. This is a slope diagram of our previous digital backend. We use this power spectrum estimation method instead of the polyphase filter banks. The reason why we do not copy this for the 4 channels because it is a power limit. The data from the ADC, we need a clock of 500 megahertz, which results in high dynamic power consumption. So this exceeds the power limitation of the chip, which is about 40 watts. So this makes the 4-channel design unattainable. So we decided to reduce the dynamic power by reduce the clock rate to 125 megahertz. However, this makes 8 data streams from ADC now becomes 32 data streams. And this increases the resource utilization, and we need optimized logical design. Now, this is a processing steps of our new backend. So we first do a windowing to mitigate the spectral leakage of fast Fourier transform. Then we do a spatial design parallel complex FFT. Then we calculate the Stokes parameters. Then we estimate the power spectrum using the Butler method. And finally, we combine the data and output in 3 modes. And we also have data width reduction unit between steps to ensure the data is always 16-bit for each step. And the processor control unit will ensure the correct data scale. And by this design, we reduce the power consumption and save hardware resources. And we want to talk more details about the parallel complex FFT. We have 2 real polarization signals input as XA and XP, and we do a combined FFT for these 2 signals. So this results in a parallel FFT with 32 complex input data streams. And the FFT results are in bit reverse mode to save the resources. and we do combined FT decomposition using a read first RAM with a size equal to FT length to get the fast FT results of XA and XB using this equation. And we finally saved about 40% LAT and 45% DRAM resources using this design. And the other processing steps is a Stokes parameter calculation. We actually calculate these 4 parameters, and the real Stokes parameter can be derived using these parameters regardless of the polarization type of the telescope. And next, we do a buttered parallelogram method, which is a classic power spectrum estimation method. And we have a configurable number of FT results to average. This allows us to adjust the time resolution. And the last step is we combine the data and output. We use this buffer RAM to prepare the 3 output modes, which is IQUV and IA plus IB and IA-IB separately. And the bit reverse FFT output order is reserved in this step. And we have 10 gigabits per second Ethernet output for each IF channel. And the four channel output is fed into a single data recording server. So we need an efficient packet capturing method. So the final result, we achieved a power consumption which is below 30 watts. And the resource utilization is shown here. As you can see, we use over 95% of DSP resources. So the resources are fully utilized. And the comparison with the other existing backend is shown here. You can see our work can handle a maximum bandwidth of 8 gigahertz from the 4 RF front ends. And the maximum frequency channels is 8,192. So we have designed a graphics control interface on the processor control unit to control the digital backend. It can be controlled through a VNC from any computer. And the first function of the control interface is to dynamically reconfigure the PL. As you can see here is the FPGA design bin file here, and we can download it into the board. And we can monitor the status of the PL, such as the temperature and the voltage. And also we can control the data scale here, and we can monitor it and set the data scale. And we also have a real-time power spectrum showing here, and a histogram plot to illustrate the distribution of signal amplitude. And we can also set observation parameters like the telescope characteristics and the pulsar information here. And we can also manage the data saving. Like here we can control the time resolution and the saving time, the output modes here, and the saving paths, and control the data saving by this button. And the data saving program is running on the data recording server, but it can be controlled by this graphical control interface through the remote SSH. So this full program is actually running in the background of the graphic control interface, and the data saving program is implemented using the DPDK, and the data is saved in the fixed format. So next part is the observation result. Our digital backend is installed on the JAMUS 66 telescope, and it is shown here. And in this application, only 3 of the 4 channels are used as shown here. And the observation result of real pulsar is also given, which validates our digital backend design. And the last part is conclusion. So we designed a compact and power-efficient digital backend solution integrated into a single IF-SOC board, and we can do a simultaneous processing of 4 signal bands with dual polarization and a total bandwidth of up to 8 gigahertz. And we offers flexible observation modes and efficient power spectrum estimation with a total power below 40 watts. And the observation experiments have validated the system's functionality and performance. Thanks for listening.
Questions?
I have 2 questions. So firstly, you mentioned the power consumption is about 30 watts. So this is only for the signal processing unit, right? Or the whole board?
This is for the board, and if we include the thermal fans, it's as below 40 watts up. As
in total.
yeah.
So say you developed your own FFT IP, right? The FFT is not using the science IP, right?
We use some of in the first we do some because the IP font settings they cannot do parallel FFT over multiple data streams. So we first use to do 512 point FFT using the settings IP to do the FFT. Then we do the base 4 FFT to combine it into 2048.
Okay, so it's still based on the science FFT IP, right?
It's further design.
Thank you, very interesting. I noticed for the number of frequency channels of 2048, your DSP usage was just on 96%. Did you have problems with closing timing for that FPGA design?
We actually have no timing errors with it too.
So say it again.
Oh,
you didn't have problems. So when you did the placement routes and had to place all the resources on the FPGA chip, did you have problems closing the timing for the frequency that you wanted the clock to run at?
The Vivado shows no timing errors on our data.
Any other questions? Then thanks once again.
Can you see is yours?
Second.
Yeah,
second.
Yes, I know that. This is still trying to open the previous talk, which didn't work. So I might just have to run back and get them to restart this.
Okay.
Because I don't see. There was any pages.
No.
Okay. And so he's gonna have to restart this. So I'll call him quickly. Just hang on a second.
All right, we'll move on to the next one.
So good afternoon. So myself Virupalagli. So I am thankful to all the co-authors, Atul Gandla, Sweta Gupta, Abhijit Dande, Sandeep Chaudhary, Ajit Kumar, and Professor Yashwant Gupta. So, so I give some introduction about the GMRT. GMRT has a 30 dishes, 30 dish 45-meter dia antennas in Y configuration. So spread over 25 kilometer. The collecting area is about 30,000 square meters. The frequency of operation is 100 megahertz to 1500 megahertz, and maximum instantaneous bandwidth is 400 megahertz. So in 100 to 1500 megahertz, we have 4 bands: band 2, band 3, band 4, and band 5. So this is about the GMRT receiver chain. So first, it has a front-end system which converts the electromagnetic waves into electrical waves, electrical signal. Then there is a feed positioning system which has a 0.5 HP motor to rotate the point the feed. One of the 4 feeds: band 2, band 3, band 4, band 5. Next one is servo system which controls and monitors the azimuth and elevation rotation of the antennas. Next, the RF signal goes to optical fiber transmitter, which has a laser diode to transmit to convert the electrical signal into light waves to transmit into the fiber optical cable. Then once the signal receives at the central electronics building, these light waves gets converted into again electrical waves by using the photodiodes. Then the signal goes to analog backend system where the signal conditioning happens and baseband conversion happens. Then the signal goes to digital backend system for digital conversion, delay correction, FFT, and correlation. So next one is a TGC, which is a Tango based GMRT control. We are calling it as it is a Tango open source code for hardware supervision and controlling. So this is developed in collaboration with the TCS, Tata Consultancy Services, under the active guidance of our Central Director, Professor Yashwant Gupta. Then to enhance the performance of our GMRT, means to fine-tune the system by removing the low-level problems, we have conducted some tests like terminating the system at various stages and injecting the broadband noise either built-in the systems for calibration purpose or external independent and correlator noise sources or CW signals. These are at various stages we have injected. This presentation mainly covers the analog and digital backend of the GMRT receiver chain. In this talk, we will discuss the low-level problems which we come across with various tests and their mitigations. First one is crosstalk. So crosstalk is a effect by the aggressor signal over the victim signal. Crosstalk is broader term of polarization leakage. Unlike EMI and RFI, crosstalk emanates within. So this crosstalk is coupled either through radiative method, radiative way, or capacitive, inductive, and conductive ways. The causes of this crosstalk are imperfection in reflector surface, non-ideal feed system, polarizer, insufficient isolation or poor shielding between the two transmission lines or circuits, means PCBs. The main sources are components and tracks on the PCBs and transmission lines as far as receiver and digital backend systems are concerned, and even connectors and all. So impacts of this crosstalk are it introduces the artifacts, errors in the output data, undesired correlation, degrade the sensitivity, reduce the dynamic range. Prevention. By following the PCB design rules, mainly for traces and components spacing, and transmission cables with good spacing, and the transmission cables with either twisted pair or shielded ones based on the frequency and amount of current flow and the length of the cable required and the environments in that particular area. So these are the main things we can consider to prevent the crosstalk. If at all it appears in the signal, then we can use valves modulation and demodulation method and some software algorithms to reduce this crosstalk. So we have in JMT we have implemented a valves modulation and demodulation. So here at the antenna base we have implemented a CPLD based 128 bits valves pattern generator, which uses the 1 MHz clock signal locked to the GMRT frequency and reference time and frequency reference. Using that, valves patterns are generated for channel 1 and channel 2. Then also it generates a sequency pulse. The sequency pulse goes to sequency modulator, and these valves patterns goes to channel 1 and channel 2 phase modulators to modulate the incoming channel signals. So once it is modulated, then the signal goes to RF filters and amplifier circuits, then other part of the GMRT chain, OFC transmitter, receiver, then analog. At this stage, the sequential pulse gets demodulated, which was modulated using the 105 MHz signal, 105 MHz. Then the RF signal goes to analog receiver system and then gets digital converted. The digital converted signal gets phase demodulation using the valves pattern, which is similar to the one used at the antenna base. So after demodulation, the signal goes to remaining part of the correlator. So this is the test results. So the blue line shows the crosstalk in C10 antennas, which was before valves implementation, and the red one which after implementing the valves modulation and demodulation. So there is a considerable reduction in the crosstalk. So next we have as far as analog and digital systems concerned, we have checked the crosstalk by using a independent noise sources. The independent noise source of 200 MHz bandwidth is inputted at two channels, either of same antenna or adjacent antennas, same polarizations or different polarizations. So then the data is recorded and plotted. So in this also we can see it was around 0.00 around 0.6% earlier, and it has reduced to around 0.4% after making improvements like some grounding, cables spacing, improving the cable spacing, and removing the cables twists and all, and connectors also were there. So with all these improvements, we get a marginal improvement in this two backends. So next one is 50 Hertz. So in India, we use electrical power up to 30 volts and 50 Hertz. So this 50 Hertz also gets interpaired with the main signal, either impedance coupling or grounding or through power supplies. So radiated means electrical lines and electrical equipments, measuring equipments, they also can radiate the electrical this 50 hertz to our main signal. So impact of this is increased noise floor, signal distortion, reduced sensitivity, data errors, and so on. So mitigation is improving the grounding, removing the ground loops, shielding of the components, cables and equipments, adaptive filtering, software techniques. These can be used to mitigate or reduce the 50 hertz. So in GMRT, we have tested this 50 hertz, presence of 50 hertz by inputting a analog noise at the analog receiver system. So this analog receiver system has a self inbuilt analog noise source, inbuilt analog noise source, which is up 200 megahertz bandwidth is inputted. So we have recorded the beamform data for single channel. Then we have used a program written by Professor Deepanjan Mitra, NCRA taper, so to analyze this data. So before showing the result, I will show why we were getting the 50 hertz in our RF signal. There was a directional coupler which was taking some portion of the main signal, means coupled output for 60-to-1 monitoring. This 60-to-1 monitoring was introduced to monitor the 60 signals of 30 antennas, dual polarization. So 60 signals to monitor one after the other for monitoring and solving the problems. For that purpose, we have introduced this 60-to-1 monitoring through directional coupler, and the main output was going to correlator. So we suspected this directional coupler. This directional coupler. So we have moved this directional coupler to the other part of the circuit where the same the signal was using for front panel monitoring purpose. So there we have moved the directional coupler to that path. So with this we have the 50 hertz got reduced drastically. This directional coupler and 50 hertz was maybe due to poor grounding of the port. This directional coupler has 4 ports. One is input, another one is main output. There are 2 more coupled ports. One is used for 60-to-1 monitoring purpose. The other one was grounded. So that through that the 50 hertz might have coupled. So that was our suspicion. Then after moving it, we have reduced the 50 hertz pickup. This plot shows the presence of 50 hertz here, presence of 50 hertz, and after mitigation, there is no 50 hertz seen here. So this right side plot shows the 600-second data, and the bottom plot shows the frequency from 0 to 1528 hertz. Then the third one is spurious pulses. Because of that 60-to-1 monitor we have introduced to monitor and debugging purpose. So we were getting some 105-second periodicity pulses. So this 105-second was matching with the switching of the 60 channels, 60 signals from 30 antennas. So we comes to know that 60-to-1 system which we have introduced is causing these signals, pulses. So for that we have separated the 60-to-1 monitor and the main signal. They were controlled by single monitor and control module. We have separated that MCM from the main signal, and we have made some software changes. And so with that, we could be able to remove these pulses introduced by the 60-to-1 monitoring. Next one is the last one is the ripples. ripples in the band. So ripples are mainly due to mismatch in the transmission line, mismatch in the impedance between source, transmission line and load. So this mismatch will cause the reflections. So if the resistive part of the resistive part should be equal, means if it is 50 ohm load, then transmission line should also have 50 ohm and source should also have 50. So all should be matched. If it is reactive part, impedance has the reactive part also. So it should be to correct that one. We should have a equal in magnitude and opposite in sign. Then higher the mismatch, means if 50 ohm goes to plus or minus 10 ohm or 20 ohm, then the amplitude will increase as the mismatch increases. Then wavelength of these ripples is directly proportional to the length of the transmission line. As the transmission line goes increasing, then the wavelength of the ripples also increases. The causes of these ripples are length and type of the cable we use, joints in the cables, connectors, if any are used in the transmission line, and nature of the load. Some loads are fluctuating, so these things causes the ripples. Impacts. So these ripples first makes the inefficient power transfer. Then signal distortion, increased noise, undesirable correlation, information error, and in some extreme cases, source also gets damaged. Then reflections and mitigation methods. So reflection, these reflections are measured mainly in as a reflection coefficient rho. So reflection coefficient is the ratio of the reflected power to the incident wave amplitudes. 0 is the no reflection and 1 is the total reflection. So if the reflected power is in watts, then this we can use this reflection coefficient. If it is in dB, then we are representing it in return loss. So return loss infinity is good, 0 is bad. Then voltage standing wave ratio. These ripples are also expressed in voltage standing wave ratio. So one is for perfect impedance matching and infinity is either open or short circuit. So the formula for this is V max by V minimum. In terms of reflection coefficient, it is 1 plus rho divided by 1 minus rho. Mitigation methods. So based on the type of transmission lines, mainly we use different types of mitigation methods. Short and open stubs are used in waveguides. Impedance matching arrays are used in normal cases, and attenuator impedance matching transformers, quarter wavelength transformers, step transmission lines are used in various applications based on the frequency and nature of environment. By considering all these things, we can choose one of the methods. So presently in GMRT we are using a attenuator method, but we are looking for a transformer method because the present attenuator method has reduced the dynamic range, and impedance matching also we want to improve it. So for that purpose we are looking for transformer method. So this is what the actual transmission line in GMRT. There is a analog receiver system in one room and digital backend system in the next room. So these two systems are connected using a RG223 50 ohm double shielded low loss coaxial cables of 15 meter length. So in between there is a connector also. These connectors are required to separate the grounding of both the systems. So here, because of as noted earlier, because of the connectors, length of the cable, and PCB design, spacing of the transmission lines, because all these factors contributed to low level ripples in the system. So causes are PCB design components, all these. Then mitigation. To mitigate these ripples present in the system, so we have used a 10 dB attenuator. So this 10 dB attenuator gives us a wide for a wideband impedance matching, but the drawback is it reduces the dynamic range. So since we have introduced a 10 dB attenuator at the distal backend side, input to the ADC, so to compensate that 10 dB loss in the signal, so we have introduced a amplifier Gali 6 amplifier which has a gain of 12 dB. So to bring it to 10 dB, we have introduced a 2 dB attenuator before that. So 2 dB attenuator plus this 12 dB amplifier gives us a net gain of 10 dB, which compensates this. Then so here we can see a low level ripples from 80 channel number 80 to channel number 550. Around this there is presence of ripples. So after implementing that ripple matching circuit, we have mitigated these ripples. Then we wanted to quantify these ripples, how much we actually succeeded in reducing. So we have used a polynomial regression method of 7th order. Why 7th order means if you go for 8th or above orders, it becomes a overfit. This pit line becomes overfitted, means that gives us the wrong result. And if it is a less than 7th order, that becomes underfit, and that also is not giving a correct result. So then after 7th order regression, coefficients we got, and after calculations, RMS is calculated of the residual signal. This is without matching hardware. This is with matching hardware. So difference of that divided by without matching hardware residual multiplied by 100 gives us the percentage of ripple reduction. So that we achieved about 75%. Even this is confirmed by using another formula, 10 log of RMS of the without matching hardware residual divided by with matching hardware residual. With this also we got same result. And we have used another method which is a 35 channel moving average method. Why 35 channel is because the width of these ripples is around 35 channels. So we have made a moving average of 35 channels. For example, if it is 118 channels, we have used 101 to 135 channels to average and get the averaged value for 118 channels. So like this, we have calculated for all the channels. Then RMS of that is calculated. With the same formula, we have got around same 75% only. So drawback, as I said earlier, the drawback of this attenuator method is dynamic range reduction. So so for this and to achieve better ripple reduction, we are going for a transformer method. So we have used a on-the-shelf matching transformer from mini circuits, but it has not met our specification. So we have asked them to give a better matching transformer which will meet our requirements and give a better ripple matching, ripple reduction. So summary is we have able to reduce the cross polar leakage and mitigate the 50 Hz interference and spurious pulses and reduce the ripples in the passband. So I am thankful to our analog colleagues, digital lab, front-end lab, control room, and Professor Deepanjan Mitra and Professor Ishwar Chandra. And I have referred all these sites for mine. Thank you.
Any good questions? We're a little bit out of time, so in the interest of time, I just thank you again.
Thank you.
All right, you good? Yeah. Give you 5 minutes. Sure. For the end, but it's not too critical. Yeah, it's fine. Yeah.
Maybe people want to go early for that. Hello everyone, I'm Kshitij. as I'm presenting this presentation on behalf of Ujjwal, who is a PhD student at NCRA India. And most part of his PhD he has dedicated to work on this project called Spotlight. Unfortunately, he couldn't be here, so I'm presenting this talk on behalf of him. So Spotlight is a new upcoming project which is happening at the GMRT, whose just introduction we heard about from Irappa. So you have a broad understanding of what is GMRT. And this is a new system that we are putting at the GMRT for searching fast and slow transients in the at low frequency ranges. Okay. So we are concentrating on fast radio bursts. Fast radio bursts are these millisecond bursts, very bright bursts that happen in the sky. They are still their origin is still a mystery. About 843 of such events have been found, and they have been detected from extremely high frequency from 8 gigahertz to as low as about 110 gigahertz. And okay. This is that there is the first FRB which was detected in 2007. They are extremely bright, about 10 to the power 36 Kelvin, which is extremely high, and believed to be of extragalactic origin because of their high dispersion measures. And there are two types. One are like repeating, and some are one-offs. Repeating FRBs was also recently discovered, and they show this kinds of very unique kind of structure, multiple components kind of structures. And first repeater was in 2016, and since then about 58 repeaters have been detected, and about hundreds of FRBs have been localized to a host galaxy. So this is an overall understanding of FRBs that we have so far. But still, as I mentioned, FRBs are still a mystery. Their high temperatures and coherent kind of emissions point towards a pulsar like of emission, but their emission is very narrow band, as you can see here. As you can see here, and also they have this multiple components present sometimes in their bursts. And also they show this drifting subburst kinds of effect, which is known as the sad trombone, like ton ton ton. That kind of effect they show in their spectra. So this is that is also shown, and they show lots of this very fine polarimetric and temporal microstructures. And progenitors of FRB are still not known, but except for one, which was this recent detection which happened from the galactic magnetar. So FRBs can act like probes because they are at cosmological distances. So when they are traveling to the interstellar medium, the intergalactic medium, you can get a lot of information about them. And also they can be used as they are having these high redshifts. They can be used as cosmological probes to study missing baryon problem, dark energy, reionization history of the universe, etc. And many of these applications required FRBs to be precisely localized. Then we can have a very statistically broad set of these localized FRBs, which can be used to study this cosmological history of the universe. So to do this, we are using the GMRT or the upgraded GMRT. As it was mentioned in the previous talk, it's a big interferometric array of about 30 antennas. Each dish is about like a 45 meters wide parabolic dish. It operates from 120 megahertz to 1.4 gigahertz. And the shortest baselines are about 100 meters, and the longest baselines are about 25 kilometers. And it is one of the most sensitive radio telescope at these low frequencies, and it is an excellent instrument for time domain applications, which can be seen here. So there have been very huge amounts of studies that have gone into follow-ups of these lots of repeating FRBs, whose locations are almost precisely known. Forest of these bursts have been detected using these FRBs. Many of the polarimetric studies have been done. Persistent radio sources have been found. There was a recent study where fast radio burst progenitor was associated with the galaxy merger, also using the GMRT. And apart from this fast radio burst, we have also there have been detections of long period transients as well as it is mentioned here, and a couple of others. So just to the point of this is GMRT is a very good follow-up instrument. Because of its good sensitivity and good resolution, it can do a very and great sensitivity. It can detect these lots of FRBs. but what it lacks is search capabilities. We are not able to search the entire sky at fast rate because the field of view is limited. And the point with the Spotlight system is to convert the GMRT from like a follow-up instrument to a primary search instrument. And the reason why we are doing this is the total FRBs detected now are about 100. Out of that, about only 14% have been localized, and we need more precise locations of more of such FRBs so that we can use them as a cosmological probe, and we can also understand try to understand what are their origins. But interferometers are good to follow up, but if we require a large sample, we need to search as bigger area in the sky as possible. And one way to do that is make use of the field of view as much as possible by forming multiple beams in the field of view. So with Spotlight, where exactly we are planning to do this, we are going to form multiple beams in the field of view, and then that can be done using a hardware such as phased array feeds, which is done in ASCAP, or in a software like a tiled beams, which is done in Meerkat. So we are going to follow the software route where we in the digital backend will form this multiple beams inside the field of view. And also GMRT is a time sharing system. It's not a dedicated telescope, so it's used for lots of other applications and used by different people all around the world. So to increase the possibility of detecting such FRBs, we will be having a commensal search. So whatever observation is going on, we will be piggybacking on that observation. Then the data, a copy of the data will be made, and we will be searching through that data to see if we see anything interesting, and then accordingly those data will be stored. So Spotlight is a commensal survey for FRBs, pulsar, RRATs, and LPTs. A dedicated backend will be created to search for these transients in real time. It is funded by National Supercomputing Mission in India. It consists of about 60 servers and about 90 A100 GPUs and capable of 1 petaflops. We will be forming about 2,000 post correlation beams in the field of view of GMRT. Post correlation beams are the beams which are formed using visibilities. They are less susceptible to RFI and systematics. You get better sensitivity. And post correlation, using these 2,000 beams, we will be localizing the FRB in real time to about arc minutes of resolution. And once there are any triggers that we found any interesting event, imaging also will be done in real time. And using that imaging, we will be further localizing that burst to arc second resolution. So in real time, we will be detecting the burst and also localizing it to about arc second of resolution. So the field of view is about 1 square degrees. The sampling, the time resolution that we get with the system is about 1.3 millisecond with 4096 channels. The bandwidths are 100, 200, or 400 megahertz depending on what the observer has set up, because as it is a commensal system, we will be dependent on what the system is set by the observer. The theoretical fluence limit is about 0.2 Jansky millisecond for signal to noise ratio of about 10. And we will be searching for single such kinds of transients for about 2000 DM in band 3, 4000 in band 4, and 8000 DM in band 5. Single pulse searches will be done for about a width of about 10 seconds, and there will be buffers of about 400 seconds of data. That means as the data is coming, the data will be stored in the buffer for 400 seconds, in which all the real-time searches, imaging, and localization will happen. And if we found something interesting, that data will be dumped, and then the next buffer will come. So that's how the system is going to work. And the predictions for the Spotlight system we have made using this FRB POPI application, where it predicts about 300 FRBs we will be detecting at this rate with GMRT. And the interesting point to note here is most of lot of these FRBs, for example, about 18% of these FRBs will be about DM of 1000. Or it can be saying that about 16% of FRBs will be above the redshift of 1. So we have a large fraction of the FRBs which might be detected with a good distances, which can be used as these cosmological probes. And this is just a comparison of FRB with some other kinds of surveys which are going on around the world. The author of this presentation has explicitly told me that this might be a old table, so some of the numbers may not be entirely true as of now. But if anyone has any additions to make, please let me know. So here we can see that Spotlight offers a very good localization accuracy and also very good fluence limits. It's very sensitive compared to other such kinds of surveys. So we are going to get a huge fraction of these FRBs which might be missed by other surveys. And this just it's a simple flow chart of the entire system. Of course, there are lots of other processes going on. We have just tried to make a simplified diagram. So the GMRT's antenna, the signal will be first coming to the GMRT antenna signal will be controlled using the control and monitoring system, because as it's a commensal system, we have to check what observations is going on, what settings are there. Accordingly, we will modify our settings and we will get the data. First, the beam tiling will happen. The beam tiling code in the field of view, it will form those 2000 beams. It will check what is the sky position, what is the time, what is the source. Accordingly, it will form an optimized beam tiling map, so that the space in the field of view is used very well. There are no wastage of the field of view, I would say. And then the correlation and the beam former will do the beam forming of this 2000 post correlation beams. And then once the beam data is there, in real time we will do all the searches for transient searches, for real time pulsar searches. We'll also do the slow pulsar searches. And once any triggers are there for any kinds of transients, that particular data will be dumped. We will be dumping the visibility data, which will be used for imaging. We will be also dumping the baseband data, which will be later used for high precision and high resolution studies of these pulses. And then once the image is confirmed, the data will be going on to a database where a human can also try to confirm if it's a real burst or not. And if it is confirmed that it's a real transient, it's a real FRB like event, then we will be doing further post studies of trying to find out the burst parameters. We will be giving external triggers such as astronomers telegram and virtual observatory events. And also we will be doing for high precision baseband studies, as I mentioned, using the raw voltage data that was dumped during that burst event. And so, as I mentioned, we are doing something called as post correlation beam forming. So this is visibilities are used to form these beams. And here there's a nice example of the impact of using visibilities. Here you can see the beam shape, which is the normal phased array beam. And here you can see the beam shape for a post correlation beam. And here it can be seen the effects of the side lobes are also reduced. The beam is also compact. And here in one of the FRB observation, where this is a normal phased array beam, and this is a post correlation beam. Here it can be clearly seen that effects of RFI compared to this here are very much reduced. And also you can see the baseline. The baseline is much more stable here in this post correlation beams, because in post correlation beam you are actually getting rid of the self term of these antennas, which causes such kind of baseline variations. And also another unique thing apart from the post correlation beam, what we are doing is we are doing something called as infill phasing or a real time phasing and calibration. Usually for any kind of radio observation, when you are observing any target source, first to find the antenna gains, you go to a phase go to a phase calibrator, get the antenna solutions, and then you move on to your target. But issue in that is, as your time goes, as you're observing the target source, your phasing solutions may not hold true. That causes the sensitivity to reduce, and also so that you may be shifting back to the calibrator, again to the source, again to the calibrator, again to the source. So you lose a lot of time on this jumping back and forth between your target and the calibrator. And there are some applications where you might require a long-term continuous scans. So one solution to do this is in-field phasing or a real-time phasing, where we use already stored model of the sky to do on-the-fly calibration. So the visibilities that are being recorded will be compared with the sky model, and we will be it's kind of like a self-calibration, but just done in real time in the system. So here is a very nice example of what is the effect of this real-time phasing. So this was one observations of a pulsar in tree with 3 different baselines. And as you can see, blue is the longest baselines, and the green is the medium baseline, and the red is the shortest baselines. So in this, even you can see in 20 minutes of the data, the signal to noise ratio of the pulsar starts to reduce because you are not doing continuously phasing. But as soon as we start doing infill phasing, where the model of the sky is generated from the first calibration scan, we start applying that infill phasing and keep doing it regularly. You can see even more than even 20 minutes, the sensitivity is constant. And in this plots, you can see even the dispersion measure error bars and also timing error bars are reduced because of this kind of infill phasing. And we are also going to do real-time imaging, as I mentioned, as soon as the visibilities are done. For that particular trigger, we know the approximate value of the DM. Based on that, those visibilities will be selected. We will be performing sort of RFI mitigation, and we will be doing the imaging, and which will be localizing the event to about arc second of resolution. And this is an example where we have actually made the real-time imaging, and it worked, and it is going on well as of now. So I'll just skip this, and we are also planning to observe pulsars with the spotlight system. One interesting thing here is for any single pulse, you just use a single pulse de-dispersion and a matching kind of studies. Of search. But for pulsars, you need to do sometime folding, which might require a longer amount of data to be required. So to do that, entire data cannot be dumped. We have to select about only 200 beams out of entire 2000 beams. So to do that, we'll be using something called as pulse scan. So pulse scan, it will find the most probable beams where any pulsars are there, and only those beams will be dumped. This is done using an unmatched Boscar filter for the Fourier transformed data. And we are also planning to do studies of long period transients using the imaging domain, where snapshot images will be made, and we will be doing the LPD searches. I'll just quickly go to the current status. The system is currently deployed with 160 beams commensal search. It is not real time yet. We are doing almost like a quasi real time, where this data is dumped, and then we are processing the data offline. Hopefully, we will be moving soon towards a complete real time observations and also 2000 beams. So far, the system is up with the observations going on in the GMRT. And here I'll just quickly wrap up with how the system was built. In May 2024, the cage was under construction, and within a few months, the data center and the first light was available we observe the crab pulsar data, and we see the giant pulses of the system, crab giant pulses through the system. And in the commensal observations that have been going on, we have detected many single pulses through lots of different pulsars. And just this is a plot of all the pulsars that we have detected. And with this plot, we can say that we are reaching our theoretical fluence limit, which is about 0.2 Jansky millisecond. So the system is performing as expected. So far, we have not detected in FRB, but hopefully, as we keep observing, we will be detecting FRBs, and these are the general broad science goals with the spotlight. We are planning to do FRBs, do cosmological studies, do pulsars, find exotic binary systems, even possibly do biosignatures using SETI kind of which is also in talks. And this is the entire spotlight. This is the part of the spotlight team, which is at the NCRA. Lots of PhD students, postdocs, faculties, interns, and I was representing this talk on behalf of them. So thank you, and please, I'll be happy to have any questions and also any suggestions, because this is a work under development. So any suggestion, any ideas will be helpful for us. Thank you.
Questions? Yes. Thank you. Very nice presentation.
Yes.
For the in-field phase calibration,
yes.
How often do you apply the calibration?
How often?
You apply the calibration.
I'm exactly not sure about that, because I have not entirely worked on it. Someone else from the team has worked on it. But as far as I remember, I think every few minutes they apply the scan. That is my rough idea, but I can get you the exact details of it. Yes.
Thanks.
Yeah.
I agree, your post-correlation beam forming has many advantages.
Yes.
But you have 2,000 beams and at full GMRT resolution, that's still only a very small fraction of the primary beam. So are you restricting?
Yes,
the
yeah.
rate
Oh, yes.
for-
Yes, yes. Sorry, I forgot to mention that. So while doing the phase correlation beam, we will be only taking the central antennas and up till the third arm antenna. So about 22 antennas out of all the 30 antennas. So we won't be taking the longest baselines. Yes.
Unused antennas, how much is the core?
So entire central core we are using.
Yeah,
And
kilometers.
yes, yeah, this is which is few kilometers. That's it. About a couple of kilometers. Yes. Thank you. I forgot to mention that, sir. Thank you for reminding me. Yes. So how that works is based on previous observations. If you already have the sky model, you will directly use that. If the sky model is not available for that particular patch of the sky, you will do the first scan. You will do the first scan of the calibration, and that will be used as a model now. And then you will be updating. So it's either the sky model is already available, or you will make in the first time, and then for subsequent observation you will use it.
Thanks again.
Thank you.
Thanks to all the speakers. It's like.
Thank you.